Hello everyone, I'm Associate Professor Dr. Sasa Arsovski. I'm a Program Director of the AI and Robotics at Raffles University. And today I will talk about novel deep learning approaches used for the brain-machine interaction. Human-computer interfaces or brain-machine interfaces will soon become a standard mode of communication with the computers. There is a lot of research conducted in this field to replace devices used to communicate with the machines, like those devices are keyboards or mouse. But today I will talk about the research that is conducted at the Raffles University, and in this research we was using the EEG brain reader to read the brain signals to communicate with the machines. But recording EEG signals is not something new. Let's say Neminsky, 1912, first recorded that animal EEG signals. Hans Berger, 1924, recorded the first human EEG. And then after that, the EEG recording techniques are developing rapidly, and in 1973, researchers defined the term brain-computer interfaces. After 2019, there was some attempts to use the brain-computer interfaces to synthesize the speech, let's say, and then on 2020, the artificial hand was used with the brain-computer interface. And this year also, I need to tell that Elon Musk started his company Neuralink. So when we are talking about brain-computer interfaces, we can distinguish the two different approaches. First approach, it's an invasive approach, and another approach is a non-invasive approach. So let's talk about research that we performed at the Raffles University. So in fact, inspiration for our research came from the neuroscience. As you can see from this slide, there is a sample topography of the cortical activity with vertical and horizontal movement. So in fact, you can conclude that some specific part of brain was activated when we are thinking about the movements. And we use, in our research, we use this property. So when we are thinking about specific movement, neurons and specific area of our brain are activated. Using EEG, we can estimate area and measure the volume of the neural activity. And in fact, with those signals, we can classify the different areas of the brain and neurons activities for every movement intention. This property is used by the deep learning models to decode imagined movements or imagined words. This is the way how we can, in fact, decode imagined movements in order to send the control to machines. So, of course, decoding EEG neural signals, it's a really complex task. And the experiment that is conducted in the Raffles University, we successfully decode the EEG recorded neural signals of the imagined directions. We built a deep learning based classifier, and using this classifier, we was able to distinguish when user think left, right, forward, or backward, and using those information, we was able to control the machines. At the start of our experiment, of course, we collect the data from our subjects using the electrode, EEG electrodes TP9, TP10, AF7 and AF8, but we was using consumer range wireless EEG reader. Of course, we faced a lot of challenges during our experiment. As you know, in fact, brain dynamics is very complex. Noise ratio is it's really high. So folding of cortex differs between any two persons. So it was very hard to create the model that will manage to decode the brain EEG signals. But we managed to overcome all challenges, and using the signal processing algorithms, we remove the artifacts and prepare signal to be used by the deep learning model. In the second stage of our research, we label EEG data and conduct the signal post-processing. And in signal post-processing, I want to share with you, it was a very interesting observation during our experiments. We try, we in fact give the subject to think left and right, and signals that we post-process in our label data set shows that in fact we have three classes, not only two classes, left and right. So we observed what is this the third class, in where we conclude that this is the noise from other neurons' activities. So it's very hard to classify intentions using the standard classifier, because our EEG reader is reading the different thoughts, because our neurons are firing all over the brain. But we managed to solve those problems, and we built the deep learning model and trained the model and achieve a really, really high accuracy of our predictions. In the third phase of our experiment, we developed the novel procedure for the collections of the real-time EEG signals and defined the procedure steps to send the command chain blocks to the machine. It is the big problem today, because we want to control machines in the real time, but time window in which we need to collect the data, process, post-process, classify the data, and send the commands to the machines, it's a very short. But with our approach, we manage to do it in the really, really short amount of time. It's about 2 seconds. As you can see in this slide, you can see our architecture. So, in fact, EEG reader wireless is connected using the Bluetooth connection with the computer, and then computer it's connected to the educational drone or educational robot using the Wi-Fi connection. We will collect, in fact, brain signals from the EEG reader. Then we will process the signals, classify the signals, and this classification, let's say left and right, will be sent as a command to the drone. Of course, complete pre-processing, feature extraction, and feature classification was done on the computer. Here we are talking about the brain-computer interfaces. Why? Because, as you can see from the given slide, investment in the brain-computer interfaces research rapidly increasing in the last few years. But brain-computer interface will become a novel approach in the communication between the humans and machines. And of course, the signal that Elon Musk also invested in Neuralink give us the hope that it will be more and more investments in the brain-computer interfaces. In fact, that we will step in the new era of communication with machines. Where we can use this technology and how we can use this technology. So, of course, different applications and studies are done with non-invasive brain-computer interfaces. We can check and or follow the pattern, sleep pattern analysis, so we can detect fatigue or the mental workload. We can perform the mental workload analysis. We can do the emotion analysis. We can control the devices, robotic arms or wheelchairs. We can also build a personal identification system using the brain waves. Very interesting approach. It's an approach called my brain, it's my password, because we can use the personal identification systems that are using our brain waves. Of course, we can use the brain waves in educational fields. Of course, we can use for the video games. And there is another wave of implementation. It is the military field, where brain-computer interfaces was used by the soldier to test and pilot the swarm on the drones. And it was done by the Defense Advanced Research Project Agency, DARPA, in United States. Of course, we can control the wheelchair. We can build the exoskeleton and control the exoskeleton using our brain waves. Of course, prosthetic control of severe disabilities such as tetraplegia and locked-in syndrome. We can use for the lie detection, drone control, robot control, or smart home appliances control. So, as you can see, we can use our brain to communicate and control the machines or create a personal identification using our brain waves. Since we finished our model and finished our experiment, we evaluated and tested our model using an educational robot hand, and we used also educational quadcopter or educational drone, and perform experiments as a proof of the concept, give us the promising result and the direction for the future research. But I need to ask you one question. Technology is available currently. So what was this biggest challenge for the commercial implementation of brain-computer interfaces? When you think about it, you will see that, in fact, you will conclude that each person has a different brain signal patterns. It's a big challenge to build a classifier model that can be used by any person. Yes, in our research at Raffles University, we solve also this challenge and make a huge step forward towards the commercial implementation of brain-computer interfaces. Of course, in the future work, we want to improve created models, and of course, as I can see the future, how I can see the future, in fact, of brain-computer interfaces. They can leverage the human input to enable the robot to dynamically learn human-like policies and act autonomously and learn from the humans. Now, at the end of my presentation, I would like to share with you a video of our experiments. Thank you.
Raffles University researchers, led by Associate Professor Dr. Sasa Arsovski, developed a novel deep learning architecture for decoding EEG brain signals. A novel approach to the analysis and processing of EEG signals has enabled direct control of machines using brainwaves. These are some of our experiments.